Okay, so let's continue on with class number 16, and here's the first example. This comes from Munson's textbook. I can't remember which edition. The lift and drag developed by a hydrofoil are to be determined through a wind tunnel test using standard air. If the full-scale tests are to be run, what is the required wind tunnel velocity corresponding to a hydrofoil velocity in seawater at 15 miles per hour? Assume Reynolds number similarity is required. So here's our first problem, trying to apply some of these ideas. And so we have a hydrofoil, which obviously is supposed to work in water, and they're saying we're going to do it, usually it'll be in seawater. And we're going to, some for a reason, use a wind tunnel. So I guess we're going to put the thing upside down, maybe. I don't know what we're going to do. Somehow we're going to test out the foil part of it. The lift and the drag. Okay, so we have Reynolds number similarity is what we're going to go with. The model, whoops, that's supposed to be M, versus the real thing. And so Reynolds number here. This is what we usually write for Reynolds number. We're gonna say there's a characteristic length of some sort. We don't know quite what it is. It might be, it could be the width or the length of the hydrofoil. Like hydrofoil usually has some type of the craft is above, and this is and like this is where the water level is, and this is running out there. So it could be this dimension or it could be that dimension right there. This is just a characteristic length. And this is what we're usually used to in Reynolds number. But we can take advantage. Most of the time, we're using a known, a liquid where we have these two parameters. So we could also look up and get what's kinematic viscosity, which is simply going to be the dynamic viscosity divided by the density. So it's a little bit easier sometimes to use that. Right, so this is what we're doing instead. And we could rewrite this out to figure out where our goal here is to find what the velocity is. What is the required wind tunnel velocity, right? So we want to find what the model velocity needs to be. So we can arrange that over there and bring everything over to the side and arrange it so that we see what these scales are, right? So here's the length of the real thing versus the length of the model. And then we have our viscosity scale. And then we multiply it by the real thing, right? So we have a one-to-one relationship, right? So it's a full scale. It's a full scale test. So that equals to 1. And we can look this up for air. This is going to be air, and this is going to be seawater. So let's look that up. Let me go to our. Let's go find our properties that we're going to get off of our exam equation sheet. We'll use that. And so I'm opening it up here. Course information and exam equation sheet. Where'd you go? Fluid mechanics equation sheet. Okay, there you go. Whoops. I don't want to take a tour. Where are you? There you go. All right. So let's see for air. No, I want to zoom. Where the frick is zoom? This is a stupid. I'm changing out. I'm getting a different one. I don't want to zoom. There it is, right over there. Okay. This is kind of pathetic. All right, so they were using miles per hour. It actually doesn't matter what units we use, right? So we could have air down below, and so my air from my model, I'm going to use. Why did I use that? Where are we? Oh yeah, I got to be careful. We have kinematic viscosity. That's why. I guess here I decided to use metric, but it doesn't matter because it's taking a ratio. So I'm going to use my 1.46 E minus 5. And then for seawater, make sure it's the same thing. Seawater, we say it's, oh, well, actually, look at that. I got the thing wrong. So let me actually use the right numbers right here. So if they're saying it's in seawater, that should be 1.17 E minus 6. All right, switching back over there. Okay. And then here we were looking for 15 miles per hour. Right. So this, as long as they're the same matter, that we're going to cancel out. So let's see what that is. It's going to be slightly different from what I have on my page. So in air, the speed, in order to have Reynolds number similarity here, we're going to go 1.46. I guess put the E5 in there. Oops, yep. And 1.17 E6. And divide and multiply by 15. And we need 187.2 miles per hour is necessary to be able to have Reynolds number similarity in this problem, and that's going to be probably a sort of an issue, right? You're going to have to make your wind tunnel pretty darn fast. That's probably a pretty hefty fan you have to go through for that. So let's take a look at another problem, because that was a short problem. So let's say you have the drag characteristics of a newly designed automobile having a maximum characteristic length of 20 feet are to be determined through a model study. All right, so the characteristics. Usually like drag is probably what we're looking at. The characteristics of both low speed, approximately 20 miles per hour, and high speed are of interest. For a series of projected model tests, an unpressurized wind tunnel that will accommodate a model with a maximum characteristic length of 4 feet is to be used. Determine the range of air velocities that would be required for the wind tunnel if Reynolds number similarity is desired. Are these velocities suitable? So not too much different from the previous one, especially since we had Reynolds number similarity here. So the model and the real thing need to be equal to each other. And so once again, let's use our kinematic viscosity instead of the version of the Reynolds number, just because neither of those things will be changing, and they say they can't change the air pressure in there. So what that could mean is we could pressurize the, and we'll see, I think there's another example coming up, where we can pressurize the wind tunnel, and then we could change the density, but that really won't affect what the viscosity is as long as the temperature hasn't changed much, right? So if you try to keep the temperature the same, so that because of ideal gas law, then viscosity is dependent mostly on temperature. So if you can have the same temperature, you can get pretty much the same viscosity in the gas. But then the pressure will change. Well, no, if the pressure changes, then the density will change. So that's the idea. That's the reason why they said you couldn't change the pressure. So if we rearrange this to find what the model needs to be, once again, we're going to get L over Lm, and then viscosity over viscosity times velocity. Well, as I mentioned, let's see, the scale is going to be 20 to 4, and as I mentioned, this means that we're going to have the same, we're having air in both things, and if they're the same temperature, then they're going to have the same viscosity. And so we could multiply by v, and what we end up with is 5 times the velocity, right? So the model needs to be 5 times. And we're saying we're going to go from 20 to 90. So the model at 20 miles per hour, corresponding to 20, is going to be equal to 100. We could do that math in your head, 100 miles per hour. Maybe that's okay. But now with a model at 90 miles an hour, right, is going to be 450 miles per hour, and that could be tough, right? So that's even worse than the previous example of 187.2 miles per hour. So the thing we're probably going to be concerned about is how close. What's our Mach number, right? Remember, 0.3 is sort of the tipping point when it comes to compressibility. So if we go ahead and look up, and let's see if we still have this up here. Do we have the speed of sound? No, we do not. But we do have the Reynolds number. So let's go with air, and let's assume that it's going to be air at 60 degrees, which is standard. So we're going to have a K of 1.4, right? Specific heat ratio. And we're going to have a gas constant, I'm writing this down, of 1,000, right? So we don't have to do the e to the 3 thing. 1,716, and remember those are foot-pounds per slug degree Rankine. So, and then also the temperature, what did I say? I think I said it was 69 degrees Fahrenheit. All right, so we can find what the speed of sound is going to be KRT. Remember, it has to be an absolute. So we're going to say that it's square root of 1.4. We can trust the units are going to work out, and I know they will as long as we use Rankine. So we're going to have our 69 plus our 460. Good thing to memorize if you haven't memorized that already. So I'm going to go to 69 times the 460 first, plus the 460. And then 1716 and 1.4. Take the square root. I get 1,127 feet per second. And then if I multiply by 3,600 seconds per hour and divide by 5,280 feet per mile, so 3,600 and 5,280 divided, I get 768.6 miles per hour is the speed of sound at that temperature, 69 degrees. So let's see what the Mach number is for this wind tunnel test. You take V over C, and 450 divided by our 768.6. And I get 0.5855, right? Which is greater than 0.3, therefore not incompressible, or can't be treated as incompressible. So this is not really a suitable, and then therefore not suitable. And remember, we're saying, like, are these velocities suitable? Explain. Well, this one's probably fine, right? You could try to test it out, right? We're 100 divided by, we already know in our head, we could just kind of like see that, yeah, that's not going to be a problem, but let's quantify it. And we can see that we're going to get 0.13, right? So this is at the 90 model, right? So it's not this is modeling for 90 miles per hour. This is fine. But at the 20 miles per hour, we get a 0.13. So that's that would be fine for that one. Okay, so we'll go move on to another video with some more examples.